The binomial distributions. In a binomial setting, trials are independent. Each trial has only two possible outcomes, which we call success or failure. The probability of success, which we call P, is the same for all trials, and the number of trials, which we call N, is fixed. The random variable of interest in a binomial setting we call X. It's the number of successes in N trials, and this has a binomial distribution with parameters N and P. And we write it in shorthand like this. X has a binomial distribution with parameters N and P. Here's an example. We have a fair tetrahedral die. That's a die with four congruent equilateral triangular faces, which are numbered 1, 2, 3, and 4. And those are all equally likely to come up when we roll. And we roll this die 5 times. We can define X as the number of 4s that we roll. And in that case, X would have a binomial distribution where N is 5 and P is 0.25, because the number of trials is 5 and the probability of rolling a 4 on any trial is 1/4 or 0.25. And we can figure out the probability distribution of X using our basic rules for multiplying probabilities of independent events and what we know about counting. So let's start with down the line here. The K can take on these values from 0, 1, 2, 3, 4, and 5. And we're looking for the probability that X takes on one of these values. Let's start with 2 right here. If X is 2, that means we have 2 successes in our 5 rolls. That is, 2 4s came up. And we can figure out the probability of that type of event happening by using our multiplication rule. There is a 0.25 chance that a 4 is going to come up. And in this event right here, a 4 comes up twice. So we can take the probability of 0.25 and square it to take care of the 2 successes. And then we have the 3 failures, which each have a chance of 0.75 of coming up. Those are the non-4s. And we multiply the 0.75 chance of failure together 3 times. And this way we have 5 separate probabilities multiplied together. 2 P's and 3 1 minus P's. Now the question is, how many ways can we get 2 successes in 5 rolls? Well, that's a little bit complicated. If you look at a list of all the possible ways that can happen, right here, you see that in 5 rolls you get 5 successes or 4 successes and a failure, and so on. And if you look around at the ones that have 2 successes in them, here is one of them. Here's one, here's one, here's one. There are a total of 10 of these strings of 5 S's and F's that have exactly 2 S's in them. And where those can occur, that can vary quite a bit. But the basic way that we would count how many ways those things could come up is like this. If you have 0, 1, 2, 3, 4, or 5 successes, the number of ways those could occur, there's 1 way to get no successes, 5 ways to get 1, 10 ways to get 2 or 3, and 5 ways to get 4, and only 1 way to get 5. These are just chooses. 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3. We're choosing, in effect, the different ways that the successes can be located within each string of 5 letters. So that's the key to all this, is those chooses. Since the 2 successes can come anywhere in the string of 5, there are 5 choose 2 ways that could work out. And you could put that in your calculator, and that would work out to be about 0.2637. If you look for the probability that X is 3, well, there are 5 positions in the strings of successes and failures, and we can choose any 3 of those positions to be occupied by successes, and we'll multiply that times the 0.25, which now is occurring 3 times, and the 0.75, which now is occurring 2 times. And we can put that in our calculator, and that would work out to be approximately 0.0879. So you see there's a pattern here. Each of these probabilities has a choose, which tells you how many ways you can get this number of successes in the string of 5 trials. And then we have the probability of success multiplied times the number of successes, or raised to the power equal to the number of successes, and the probability of a failure raised to the power of the number of failures. So if we follow this pattern, we can fill in this list right here. For 0 successes, we have 5 choose 0 ways that can happen, and that's just one. We have 0.25 probability of success raised to the 0 power. That is just one. And then we have 0.75, the probability of failure raised to the 5th power. So this is what you would get if you just used your basic rules of probability and said, well, I can get a non-4 and a non-4 and a non-4 and a non-4 and a non-4. A string of 5 non-4s, well, each of those probabilities would be 0.75, and we would just multiply them together because the outcomes are independent. And this will be approximately 0.2373, and the probability of getting one success, that is 1 4 in our string of 5 rolls, would be 5 choose 1, because that success could happen in any of the 5 positions, times 0.25 to the 1st power, we have one success, and 0.75 to the 4th power, because we have 4 failures. And we multiply those together, and we get 0.3955. Now you can see the pattern here of how these things work. We have a choose, the probability of success raised to some power. That power happens to be equal to the number of successes we're interested in. And then we have the probability of failure raised to a power. And these two powers add up to the number of trials, 5. So there's a pattern to this. I want you to follow that pattern, and you can pause your video and follow that pattern and figure these out. Okay, welcome back. The probability that x equals 4 is 5 choose 4 times 0.25 to the 4th power times 0.75 to the 1st power, because in this situation we have 4 successes, 1 failure, and that those 4 successes, the 1 failure rather, can appear in any of the 5 positions in the string of 5 outcomes, and this works out to be 0.0146, and then 5, the probability that x is 5 choose 5, which is 1, times 0.25 to the 5th power times 0.75 to the 0 power, and when we multiply that together we get approximately 0.0010. So there's a pattern to this, and you can follow that pattern whenever you're working with these things. Binomial probabilities are they're kind of nice because they do follow that kind of pattern. Now you can calculate binomial probabilities on your calculator. If you want to calculate a probability of a particular outcome, such as in one of these situations, well, you can just go second vars and get into the distribution menu, and then scroll down to Binomial PDF. This is in a different location depending on what kind of calculator you have, TI-83 or TI-84. But you're going to select Binomial PDF, and then the syntax here is to put in the number of trials. In this case it's 5. The probability of success, in this case it's 0.25, and then the number of successes you're interested in your 5 trials. For instance, if we look at 2 successes, there it is, 0.2637, which is what we got when we did it by hand. If you want to find the binomial probability for 3 successes, well, a similar deal. Pick Binomial PDF, put in the number of trials, the probability of success on any given trial, and the number of successes we're interested in, and press enter, and there it is, 0.0879, which is what we got when we did it this way. Now you could calculate all these probabilities in a row. It's very easy. What you do is go to your stat editor and you put in the values of k, 0, 1, 2, 3, 4, 5. And then we can fill up the second list right here with the binomial probabilities. And it's pretty simple to do. Quit out of there and then go second vars, go down to binomial PDF, put in 5, 0.25, and then instead of a specific value for k, what you put in here is list 1. So you go second of 1 and put in list 1, and then we can store that in list 2. And then the calculator will calculate all the probabilities at once, and if you want to look at them, you just go into Stat Edit, and there they are. Okay, so that's a nice feature. You can also make a probability histogram from these numbers if you set up your stat plot so that it's a histogram right here, and you make your X list be L1, which is where the values of K are, and make your frequency list be L2, where the probabilities are. Then you can draw this graph, and here's the probability histogram for this situation. You see it's fairly strongly right skewed, and it's going to have its peak over here at k equals 1, and we saw that in the numbers here in the probabilities we looked at. The highest one was here when k equals 1, and you can make that. Now there's one trick to this. You need to set up your window so it's going to behave correctly. If you let the calculator set up the window, it might make a mess of things, but if you do it yourself, set it up so that your x min is negative 0.5 and your x max is 0.5 greater than the number of trials. So we have enough room for 6 bars, and make each bar 1 unit wide. And then if you know roughly where your probabilities are going to wind up, you can make your y's run from about negative 0.1 to say positive 0.4. That's going to vary from situation to situation, but you can experiment with that and make your y-scale be 0.1, and then when you draw the graph, it comes out looking the way a probability histogram should look. So the syntax again for working with the calculator is like this. On a TI-84, it would be second vars A, binomial PDF, and then you plug in the values for NP and K in here. The calculator will give you the binomial probability that you want. The calculator can also do cumulative probabilities. Say you want the calculator to find the sum of several binomial probabilities. Say you want the calculator to find maybe the sum of these first 3. Well, you could calculate them individually and then add them up, or the calculator has something built into it called binomial CDF, which is a cumulative probability calculator. And so you go second vars and then go down just below binomial PDF is binomial CDF, and then you put in your N, your P, and your K. For instance, say we want 5 trials, 0.25 probability of success on a trial, and we want to add up these first 3 probabilities, the probabilities up to and including k equals 2. You put in 2 in there, and it calculates the sum of those 3 directly. Now when you're working with large values of n and maybe large values of k, this is going to be very useful because it saves you a lot of time.